Hello everyone. In this video, I'm gonna go through the properties of determinant. This is the second video of uh, the determinant lecture video determinant. So here's a question: how does the determinant A change when row operations are performed? So this, the, the answer is this: if a multiple of one row of A is added to another row, that's the one of the row operations, right? So there are three row operations. So this is the one of the row operations. So then determine A is not changed. Okay, so multiple of one row of A is added to the other row. Then determine A that one will not affect the determine A. Okay. So if two rows are interchanged, the determinant A change to negative determinant A. So if you just change the rows, then the sign of determinant A will be changed to opposite. So and then if one row of A is multiplied by K, then determinant A is changed to K times determinant A. So even if even if you the multiply the scalar multiply the just one single row by a scalar, then determine A will be the multiplied by K. Okay, so keep in mind that. So let's see example. 3 by 3 matrix given. Okay, and then compute determine A. Okay, so then yeah, you can use the cofactor expansion. Okay, so but let me just reduce the matrix A to echelon form. So we're gonna get the upper triangular matrix. Then the last time, I mean, the determinant, the lecture video part 1, we learned that what the determinant of triangular matrix is the product of the main diagonal entries, right? So to use that, I'm gonna reduce the matrix A to echelon form. Okay, so now then determine A from here is gonna be which is this denoted by this, right? So now I'll just make 0 for that three entries, so that we're gonna get the upper triangular matrix. This is the process that we get the echelon form of matrix A. Okay, then what are we gonna do? We're gonna use the first row to make the these two entry to 0. Okay, so first what we're gonna do, to make this 0, we need to multiply the first row by -2 and then adding them into the second row. Okay, so we replace the second row by this one. Okay, so we got this. And then now to make the 0 this entry, we gonna do this one, perform that row operations, negative R1 plus R3, and then put them in, substitute this one into R3 sub 3. Okay, which means replacing the third row with the negative R1 plus R3. Okay, so now then we got this. You see this? This is upper triangular matrices, and then you can see that these are pivot. Okay, so there are 3 pivot, non-zero pivot, which is exactly the same as the number of column in matrix A, which means that matrix A is invertible. As you can see that this is upper triangle, and also this is a triangular matrix. Okay, and then by the way, so then we got this one. By the way, I skipped the one step. We got this one, and then I just interchange the second row and the third row. Okay, so to get the triangular matrix, if you interchange the row, then what? The sign of determinant will change, right? That's why I put the negative sign. And now then we got this 1, 3, and negative 1 times 3 times negative 5, because this is a triangular matrix. Okay, determinant triangular matrix is this, which is 15. Okay, so determine A, the determinant of the square matrix A can be can be written as like this: negative 1 to the R times the product of main diagonal di. Okay, So here di is actually pivot. Okay, so reducing matrix A to the echelon form. Okay, then we might apply the one of the row operations, interchanging rows r times. That's why -1 to the r is here. Okay, the di is after completing the reducing matrix A to the echelon form, we get these pivot. So di represent pivot. Okay, so so when r is invertible, the term A can be expressed as like this. It's much what the easier to find the term A using cofactor expansion, right? But what if A is not invertible? Then well, A is not invertible, which means that number of pivot is less than number of column, which means that one of diagonal entry, when you reduce matrix A to the echelon form, the sum of them or one of them, and this the one diagonal entry must be 0. That's why determinant A is 0. That's why a square matrix A is invertible if and only if determinant A is not equal to 0. Okay, so let's see other theorems. If A is an n by n matrix, then determinant A transpose is equal to determinant matrix A. Why? Let's see. Let's say matrix A, n by n square matrix A is given like this, okay? And then determine A using the cofactor expansion of matrix A across first row is this, right? Okay, so now then that is equal to the cofactor expansion of matrix A down the first column, see? So, but if you just determine A is what? But actually what this one can be considered as the determinant of A transpose, right? Okay, that is also equal to a cofactor expansion of A transpose across the first row, is it? Okay, and then but determine A, if you just when you find the determinant A, we just find the apply the cofactor expansion in the first row or first column. Okay, either way we're going to get the same value of determinant A. Okay, so that's why determinant A is equal to determinant of A transpose. Okay, so that's why that theorem holds. Okay, so the property the you know the property of determinant as well as these two theorems. Okay, just keep in mind this. So that's for today.